expected to double by 2050 due to its role in electric vehicles, sustainable packaging, and renewable energy. Advanced insights into aluminum production in a factory. Now that we've covered the essential steps of aluminum production, let's go even deeper into the science, engineering, and technological advancements shaping the industry. 1. Advanced bauxite processing and refining technologies. Challenges in bauxite mining and processing. Declining ore quality. Many aluminum production in a factory. Producing aluminum in a factory is a complex industrial process that involves multiple steps, from raw material extraction to refining and smelting. Here's how it works. 1. Raw material extraction. The primary source of aluminum is bauxite ore, which is mined from open pit or underground mines. Bauxite contains aluminum oxide, AlCO, along with impurities like silica, iron oxides, and titanium dioxide. 2. Refining. Bayer process. Bauxite is crushed and mixed with hot sodium hydroxide, NaO, and high-pressure This process dissolves aluminum oxide into alumina AlCO, while leaving impurities as red mud. The alumina is then filtered, precipitated, and heated in a kiln at 1000 to 1200 degrees Celsius to form a white powder. 3. Smelting. Whole H process. Alumina is dissolved in molten cryolite NOLFKs, in large electrolytic cells. A strong electric current is passed through carbon electrodes, causing aluminum to separate and sink to the bottom of the cell. This process happens at around 950–980 degrees Celsius, and is highly energy-intensive for casting and rolling. The molten aluminum is poured into molds to form ingots, slabs, billets, or rods. These can be further processed through rolling, extrusion, or forging to create sheets, wires, or structural components. 5. Recycling and sustainability. Recycling aluminum uses only 5% of the energy needed for primary production, making it an eco-friendly material. Aluminum scrap is melted down and reused without losing its quality. Applications of aluminum: automotive and aerospace, lightweight but strong, construction, windows, frames, and bridges, electronics, conductive and packaging, cans, foils, and food containers. In-depth aluminum production process. Producing aluminum in a factory is a large-scale industrial operation that requires mining, refining, smelting, and shaping. Here's a more detailed breakdown of each stage. 1. Bauxite mining and transport. Aluminum is extracted from bauxite ore, which is mainly found in tropical and subtropical regions, Australia, Guinea, Brazil, etc. Mining methods. Open pit mining most common, underground mining rare. The mined bauxite is transported to refineries via trucks, trains, or conveyor belts. Refining. Bayer process. The Bayer process is used to extract alumina AlCO from bauxite. Step-by-step process. Crushing and grinding. Bauxite is crushed into small particles. Digestion. The crushed bauxite is mixed with hot sodium hydroxide NaO at high pressure, 30 to 50 atmospheres, and 150–200 degrees Celsius. Separation. The aluminum oxide dissolves, while impurities red mud settle. Precipitation. The aluminum hydroxide is extracted by cooling and stirring the solution. Calcination. The aluminum hydroxide is heated to 1000 to 1200 degrees Celsius, turning it into pure alumina AlCO. Byproduct. Red mud, a toxic waste, must be carefully managed to avoid environmental damage. 3. Smelting hall process. The hall process extracts pure aluminum from alumina using electrolysis. Step-by-step process. Electrolytic cells. Large carbon-lined cells, also called reduction pots, hold molten cryolite NOLFKs and dissolved alumina. Electrolysis begins. A huge electric current 4 to 5 volts, but up to 300,000 amps, is passed through the cells. Reaction. The oxygen in alumina bonds with carbon electrodes to form carbon dioxide, C. The aluminum separates and sinks to the bottom as a molten metal. Extraction. The molten aluminum is siphoned out and sent for casting. Energy use. This process consumes 15,000 kilowatt-hours per ton of aluminum, making energy efficiency a key factor in aluminum production. For casting and rolling. Casting. The molten aluminum is poured into molds to form ingots, billets, or slabs. Rolling and extrusion. The metal is shaped into sheets, rods, or structural parts through rolling mills or extrusion presses. Aluminum is mixed with copper, magnesium, silicon, or zinc to improve strength and durability. 5. Recycling and sustainability. Recycling aluminum saves 95% of the energy used in primary production. Scrap aluminum is melted and reprocessed without losing quality. Many industries, automotive, packaging, aerospace, rely heavily on recycled aluminum. Challenges in aluminum production. High energy consumption. Smelting requires vast amounts of electricity. Environmental impact. Red mud disposal and carbon emissions must be managed. Raw material supply. Mining bauxite can cause deforestation and habitat destruction. Full breakdown of aluminum production in a factory. Aluminum production is one of the most energy-intensive industrial processes, involving several complex steps. Let's go even deeper into the science, engineering, and challenges behind each stage. 1. Bauxite mining and raw material processing. Bauxite is the primary raw material for aluminum, and it contains 30 to 60% aluminum oxide, alco, along with impurities like iron oxides and silica. Mining techniques. Open pit mining. Used in most aluminum-producing countries, Australia, Guinea, Brazil, China. Large bulldozers, excavators, and haul trucks extract the ore. Underground mining. Rare but used where bauxite deposits are deep underground. Processing before refining. Crushing and washing. The raw bauxite is crushed into smaller pieces and washed to remove clay and other unwanted materials. Drying. The ore is dried before transportation to refineries. 2. Refining Bayer process. Extracting alumina. The Bayer process, developed in 1888, is still the primary method of refining bauxite into alumina alco. Step-by-step breakdown. Grinding and mixing. The crushed bauxite is mixed with hot sodium hydroxide NaO at 3250 bars pressure and 150-200 degrees Celsius. This dissolves aluminum oxide but leaves impurities behind. Separation, settling, and filtration. The red mud iron oxides, silica, and titanium dioxide settles to the bottom and is removed. The liquid solution contains dissolved sodium aluminate, Na-AlO-G, precipitation. The solution is cooled, and aluminum hydroxide aloe starts to crystallize out. Calcination. The aluminum hydroxide is heated to 1000 to 1200 degrees Celsius in rotary kiln. This removes water, leaving behind pure alumina alco, in white powder form. Environmental issues of the Bayer process. Red mud waste, highly alkaline and difficult to dispose of. Some research focuses on repurposing it for construction materials. Energy consumption. Requires high temperatures, increasing the factory's carbon footprint. 3. Smelting hall process. Smelting is where aluminum metal is extracted from alumina, using electrolysis, a process invented in 1886. Key equipment used in smelting factories. Electrolytic cells reduction pots, large carbon-lined containers that hold molten cryolite NaOF keys and alumina. Carbon electrodes, anodes plus, made of carbon, slowly consumed during electrolysis. Cathodes lined inside the pots, collecting molten aluminum. How electrolysis works. Dissolving pure alumina alco is dissolved in molten cryolite at around 950-980 degrees Celsius. Cryolite lowers the melting point of alumina, reducing energy costs. Applying electric current. A direct current DC of up to 300,000 amps is passed through the molten mixture. At the anode plus, oxygen reacts with carbon, producing co-gas. At the cathode, pure aluminum metal forms and sinks to the bottom. Tapping the aluminum. Every few hours, the molten aluminum is siphoned off and transported to casting furnaces. Each electrolytic cell can produce 1 to 2 tons of aluminum per day. Energy requirements. Producing 1 ton of aluminum requires about 15,000 kilowatt-hours of electricity, which is why aluminum plants are often near hydroelectric power stations. For casting and forming the final product. Once the aluminum is extracted, it must be shaped into usable forms. Types of casting methods. Ingot casting. The molten aluminum is poured into ingot molds for storage and transportation, later remelted for further processing. Continuous casting and rolling. The molten metal is cooled and stretched into thin sheets or plates, used for making foil, beverage cans, car bodies, and aircraft parts. Extrusion. Aluminum is forced through a die to create complex cross-sections, for example, window frames, railings, heat sinks. Forging. Aluminum is shaped under high pressure into strong structural components, for example, aircraft landing gears. Powder metallurgy. Aluminum powder is compacted and sintered for high-strength industrial applications, 5. Recycling and secondary aluminum production. Why recycle aluminum? Energy savings. Recycling aluminum uses only 5% of the energy needed for primary production. Aluminum can be recycled without losing quality. Environmental impact. Reduces the need for bauxite mining and smelting emissions. How aluminum recycling works. Collection. Scraps, cans, car parts, old aircraft are gathered and sorted. Shredding and cleaning. Contaminants, paints, plastics are removed. Melting. The clean aluminum is melted in large furnaces. Casting and rolling. The molten aluminum is cast into ingots, sheets, or billets for reuse. Recycled aluminum accounts for over 75% of the aluminum in use today. Challenges and future innovations. 1. Reducing energy consumption. Smelting with renewable energy sources, solar, hydro, wind. Developing inert anodes to reduce CO emissions. 2. Sustainable red mud disposal. Research on converting red mud into cement or ceramics to reduce waste. 3. Advancing lightweight aluminum alloys. High-strength aluminum lithium alloys for aerospace. Aluminum magnesium alloys for car bodies to improve fuel efficiency. For next-gen smelting, carbothermic reduction. A potential alternative to the whole H process that could cut energy use by 30 to 50%. Conclusion. Why aluminum is crucial. Lightweight and strong. Essential for aerospace, automotive, and construction. Corrosion resistant, used in marine and industrial applications. Eco-friendly, highly recyclable, reducing environmental impact. High demand. Global aluminum demand is expected to double by 2050 due to its role in electric vehicles. Sustainable packaging and renewable energy. Advanced insights into aluminum production in a factory. Now that we've covered the essential steps of aluminum production, let's go even deeper into the science, engineering, and technological advancements shaping the industry. 1. Advanced bauxite processing and refining technologies. Challenges in bauxite mining and processing. Declining ore quality. Many high-grade bauxite reserves are depleting, forcing companies to process lower-grade ores, which requires more energy. Environmental concerns. Mining leads to deforestation, water pollution, and biodiversity loss. Energy-intensive process. The Bayer process consumes 3 gigajoules of energy per ton of alumina. Emerging refining technologies. Direct alumina extraction from clays. Researchers are exploring extracting aluminum directly from kaolin clay, reducing dependence on bauxite mining. This method eliminates the need for the Bayer process and could cut energy use by 30%. Red mud recycling. Scientists are developing ways to recover iron, titanium, and rare earth metals from red mud, turning waste into valuable resources. Some companies use red mud as a raw material for cement, using bacteria to break down red mud's toxic compounds, reducing its environmental impact. 2. Cutting-edge smelting technologies. The Hall process has been the standard since 1886, but it's highly energy-intensive and produces large amounts of CO. Key challenges in traditional smelting. High energy demand. Requires 15,000 kilowatt-hours per ton of aluminum. Carbon emissions. The anodes used in electrolysis are made of carbon, leading to 2 tons of CO emissions per ton of aluminum. Innovations in smelting. Inert anode technology developed by Elysis and Alco Rio Tinto. Instead of using carbon anodes, which release CO, inert anodes release oxygen O, making the process carbon-free. Expected to cut global aluminum industry emissions by 7%. Already in early production for Apple's MacBook casings. Carbothermic reduction. Instead of electrolysis, aluminum is extracted using carbon in high heat, those mil grados. Reduces energy use by 30 to 50% and eliminates cryolite. Still in research phase, but has potential for massive industry disruption. Microwave smelting. Some experiments show that microwaves could heat aluminum, or more efficiently, cutting energy use. Not yet commercialized but could revolutionize aluminum production. 3. Ultra-high-performance aluminum alloys. Aluminum alloys are critical in automotive, aerospace, and military applications. The industry is constantly developing stronger, lighter, and more heat-resistant alloys. Next-gen aluminum alloys. Aluminum lithium alloys, 25% lighter than standard aluminum. Used in SpaceX rockets, Boeing 787 Dreamliner, and next-gen fighter jets. Aluminum magnesium alloys. Extremely corrosion resistant, ideal for marine applications and lightweight vehicles. Tesla and BMW are using these alloys in electric car frames. Superplastic aluminum. can be stretched up to 200% before breaking. Used in lightweight aircraft bodies and high-performance bike frames. Transparent aluminum Elan aluminum oxynitride, harder than bulletproof glass but half the weight. Used in military armor, spacecraft windows, and laser systems. For smart factories and AI-driven aluminum production. Modern aluminum factories are integrating Industry 4.0 technologies to boost efficiency. How AI and automation are transforming aluminum manufacturing. Predictive maintenance. AI monitors equipment performance, predicting failures before they happen, reduces downtime and maintenance costs. Real-time process optimization. Machine learning adjusts temperature, voltage, and raw material inputs for maximum efficiency. Automated quality control. AI-driven vision systems detect microscopic defects in aluminum sheets before they reach customers. Autonomous transport systems. Self-driving trucks and conveyor belts move raw materials and finished products within factories. 5. Sustainable aluminum production and circular economy. Eco-friendly aluminum innovations. Carbon-neutral aluminum. Companies like Hydro and Rio Tinto now produce green aluminum using hydroelectric power instead of fossil fuels. Carbon footprint is reduced by 75% compared to traditional smelting. Hydrogen-powered aluminum plants. Some factories are experimenting with hydrogen as a heat source, replacing natural gas. 100% recycled aluminum products. Beverage companies are shifting toward fully recycled aluminum cans. Ford and GM recycle their own aluminum scraps to make new car parts. How much aluminum is recycled? 75% of all aluminum ever produced is still in use today due to its recyclability. Recycled aluminum only requires 5% of the energy of primary production. The goal is to reach 90% plus recycling rates worldwide by 2050. 6. The future of aluminum. What's next? 1. Space-grade aluminum for interstellar missions. NASA is developing radiation-resistant aluminum alloys for Mars and deep space exploration. SpaceX's Starship incorporates aluminum-lithium alloys for reusability. 2. Graphene aluminum composites. Scientists are experimenting with graphene-infused aluminum, which is 300% stronger and more heat-resistant. Could replace titanium in aerospace and military applications. 3. Self-healing aluminum. Researchers are testing aluminum that repairs microscopic cracks using embedded nano. This would dramatically increase lifespan and durability. For aluminum-air batteries, alternative to lithium-ion batteries, potentially powering EVs for 1,500 plus miles on a single charge. Produces electricity by reacting aluminum with oxygen. Could replace traditional EV batteries by 2035. Conclusion. Why aluminum will dominate the 21st century. Lightweight, strong, and versatile. Used in everything from smartphones to skyscrapers. Eco-friendly and recyclable. 75% of aluminum is still in use today. Critical for the future. Space exploration, EVs, and green energy depend on advanced aluminum tech. Innovation-driven AI, 3D printing, and superalloys will redefine its applications. The ultimate deep dive into aluminum production. We've covered the basics and advanced aspects of aluminum production. Now, let's push even further into next-generation manufacturing, futuristic applications, and the challenges shaping the industry's future. 1. Ultra-high-efficiency aluminum smelting. While the Hall process has been the industry standard for over a century, cutting-edge alternatives are emerging to make aluminum production cheaper, cleaner, and more energy. 1.1 Molten oxide electrolysis, MO, the future of aluminum smelting. Developed by Boston Metal, this process eliminates carbon anodes, reducing emissions to zero. Instead of carbon, MO uses inert metal anodes, producing pure oxygen as a byproduct. Can work with low-grade bauxite ores, reducing waste. Energy demand is 40% lower than the Hall-Etch process. Impact. If widely adopted, this could cut global aluminum industry emissions by 80%. 1 point to direct aluminum extraction from clays kaolinite. Traditional aluminum production depends on bauxite, but some regions lack high-grade bauxite deposits. Scientists are now extracting aluminum from common clays instead. Advantages. More abundant than bauxite found in many countries. No red mud waste, reducing environmental impact. Lower energy consumption. Uses a direct acid leaching process instead of biorefining. Potential. This method could open up aluminum production in new regions, lowering global costs. 2. Advanced alloy development, stronger, lighter, smarter. 2.1 High-entropy aluminum alloys. Here, a revolutionary category of materials that combine aluminum with multiple metals, creating alloys with unparalleled strength and heat resistance. Uses in aerospace and defense. 5x stronger than conventional aluminum, can withstand temperatures over 900 degrees Celsius, compared to 660 degrees Celsius for standard aluminum. Shock-resistant and corrosion-proof, perfect for hypersonic missiles, space stations, and advanced armor. Challenges: expensive to produce, still in early research, difficult to mass manufacture. Complex atomic structures make industrial-scale casting tricky. To point to self-healing aluminum. The next leap in materials science. Researchers are developing aluminum alloys that can repair microscopic cracks on their own, using embedded nano. How it works. When exposed to oxygen, the alloy releases a self-sealing chemical reaction that fills in inspired by biological healing in human bones. Applications. Aerospace reduces maintenance for spacecraft and satellites. Bridges and skyscrapers. Extends structural lifespan. Automotive. Cars would last twice as long with minimal wear. 3. The role of AI and robotics in smart aluminum factories. 3.1 AI-driven predictive maintenance. Sensors in aluminum plants monitor equipment in real time. AI predicts when machines will fail, reducing downtime by 50%. Example: Tesla's gigafactories use AI to optimize casting and aluminum extrusion processes. 3.2 Fully automated aluminum casting. Factories are moving toward robotic-controlled aluminum pouring and mold design. Precision laser scanners ensure zero defects in each cast. AI helps optimize mold designs, reducing scrap waste by 30%. For aluminum in electric vehicles and battery technology. 4.1 The rise of aluminum-air batteries. A potential game-changer for EVs, aluminum-air alloy batteries could extend driving ranges to over 1,500 miles per charge. How it works. Aluminum reacts with oxygen, creating electricity without needing lithium. Produces 10x the energy density of lithium-ion batteries. Advantages. Lightweight, perfect for aviation and military applications. Cheaper than lithium. Aluminum is 50x more abundant. 100% recyclable. No toxic metals involved. Challenges. Rechargeability. Currently not rechargeable, but researchers are working on making aluminum-air batteries recyclable on site. 4.2 Aluminum's role in lighter, more efficient EVs. Why automakers love aluminum. Stronger than steel but 60% lighter. Corrosion resistant, perfect for harsh climates. Easier to shape into complex designs for aerodynamics. Which companies are using aluminum? Tesla Model S Plaid. Full aluminum frame for lightweight speed. Porsche Taycan. Aluminum body for high energy efficiency. Ford F-150 Lightning. First mass-produced aluminum truck. 5. Recycling breakthroughs and the circular economy. 5.1 Next-gen aluminum recycling. Electromagnetic sorting. Uses AI-powered sensors to separate high-purity aluminum from scrap waste. Molten salt electrolysis. A new process that extracts aluminum from dirty scrap at near-zero energy loss. Nano-coating removal. Uses plasma to strip paints and coatings without harmful chemicals. Target. By 2035. The goal is to produce 90% of aluminum from recycled sources, eliminating the need for new mining. 6. The next 50 years of aluminum. Predictions for 2075. 2030. Fully AI-powered aluminum plants with zero waste. 2035. Aluminum air, batteries, power next-gen, EVs, and aircraft. 2040. Space habitats and lunar bases built with self-healing aluminum. 2050. Smart aluminum structures that adapt to extreme environments, for example, underwater cities, Mars colonies. 2075. Ultra-lightweight aluminum alloys replace steel in skyscrapers, doubling building heights. Conclusion. Why aluminum will shape the future. Most recyclable metal, key to a sustainable, circular economy, essential for green energy. Used in solar panels, wind turbines, and lightweight EVs, vital for space exploration. Light, strong, radiation, constantly evolving. New alloys, batteries, and AI-driven production methods. The ultimate guide to aluminum, production, innovation, and the future. Aluminum is one of the most versatile, recyclable, and essential metals in modern industry. From cars and airplanes to spacecraft and batteries, aluminum is shaping the future. This guide covers everything about aluminum from traditional manufacturing to cutting-edge innovations. 1. Aluminum production from ore to metal. 1.1 Mining and refining bauxite. Aluminum starts as bauxite ore, found in tropical regions. Major producers: Australia, Guinea, China, and Brazil. Refining process. The Bayer process extracts alumina alco from bauxite. Waste problem. Red mud, a toxic byproduct, is a major environmental issue. Next-gen solutions. Red mud recycling extracting iron and rare earth metals. Alternative ores. Kaolinite clay for aluminum extraction. EDR smelting aluminum hull process. Electricity-intensive process, 15,000 kilowatt-hours per ton of aluminum. Carbon anodes burn, releasing CO. Major producers: China, India, Russia, and Canada. New smelting technologies. Inert anodes releases oxygen instead of CO. Molten oxide electrolysis (MO) uses metal anodes for carbon-free smelting. Microwave smelting uses microwaves to heat aluminum or more efficiently. Goal: carbon-free aluminum production by 2050. 2. Advanced aluminum alloys. Stronger, lighter, smarter. 2.1 High-strength aerospace alloys. Aluminum lithium alloys, 225% lighter. Used in rockets and space stations. Superplastic aluminum. Can stretch 200% without breaking. Transparent aluminum alloy. Used in military armor and laser tech. 2.2 Smart and self-healing aluminum. Nanoparticle-infused aluminum repairs microscopic cracks on its own. Reduces maintenance for aircraft, cars, and bridges. Future uses: Mars habitats, deep-sea exploration, and military exoskeletons. 3. AI and robotics and smart aluminum factories. AI-powered quality control. Detects defects in microseconds. Autonomous casting systems. Robots pour and shape aluminum molds with precision. Predictive maintenance. Sensors prevent breakdowns before they happen. AI-optimized recycling. Machine learning sorts and purifies aluminum scrap. Example: Tesla's Gigapress, a high-pressure aluminum casting machine for building entire car frames in seconds. 4. Aluminum in electric vehicles and battery tech. 4.1 Aluminum air batteries. The next EV revolution. 10x energy density of lithium, 1,500 plus miles per charge. 100% recyclable. Challenges: not rechargeable yet, but research is ongoing. Future: could replace lithium-ion batteries by 2035. 4.2 Lightweight aluminum car frames. Tesla Model S Plaid. Full aluminum frame. Porsche Taycan and Audi e-tron. Use aluminum for weight savings. Ford F-150 Lightning. First aluminum-bodied electric truck. 5. Recycling in the circular economy. 5.1 Next-gen aluminum recycling. Electromagnetic sorting. AI identifies high-purity aluminum. Molten salt electrolysis. Extracts pure aluminum from dirty scrap. Nano-coating removal uses plasma to strip paint and coatings without waste. Goal: 90% plus global aluminum recycling rates by 2050. 6. The future of aluminum. 2050 and beyond. 2030. AI-powered, carbon-free aluminum factories. 2035. Aluminum air batteries replace lithium in EV. Impact: recycling aluminum saves 95% of the energy compared to new production. 2040. Lunar base is built with aluminum alloys. 2050. Smart aluminum structures adapt to extreme environments. 2075. Skyscrapers twice as tall, built with graphene aluminum composites.